from Globebusters.
Okay, yeah. I get your point. Yes, you can. I can take a picture of my street and then turn to the left and take another picture and put them together. And I guess that is a real thing. But if you're starting to try and prove things with those images, well, then you can understand when somebody says, well, that's a composite, that could be taken from high altitude planes and then wrapped on a sphere, which, believe it or not, is exactly what they say they do.
Yeah. And if you let me, I'll get really technical here, but be really precise about it. With maps and images, only a flat Earth is a differentiable manifold, meaning at any level of detail, you have a matching topography with zero variance. So if you piece together maps or you piece together images, you get a flat Earth, for as far as I know. Now, I looked into what they do about topography, because we know that, like, Google Earth takes the flat maps and wraps it around a normalized sphere, not even an oblate spheroid, but I think they use a perfect sphere geometry still at this point. And I remember when Microsoft, it was like the flight simulator had an update, and they put in a ton of code in order to wrap their map around and make it a spherical gaming plane or a gaming world. But it was still a plane. It just had this adjustment to it, just like many of the video games all have flat maps. And I found this course. It's an advanced course, and they have a syllabus for it. And they talk about differential topology. And basically, to pass the course, you have to go through learning about how to do this and the proof that you need to do to pass it. It's an inductive procedure. It's a relative approximation result for maps between open subsets of Euclidean spaces. So what they use is what they call convolution kernels. And then so at the midterm, they're using subsets of manifolds to measure with zero variance at selected points. And so what they do is they rank the topography of each map, and they select nodes or points to match up with zero variance. And then they have vertical derivatives as you go away from those points. And so what they do is they use calculus and they map out the curvature. And then they use these variable, they call them isotopies, or they restrict it to a neighborhood or a zone within the elevations so they can zero the section out. And so they write a program that creates kind of an automorphism to normalize the bundle. So that's the language they use, but they are basically forcing the flat maps around. And that's what I saw with Google Earth. When you zoom in and you get to a level of detail where it's going to match a navigable map that you could use to measure distances with high precision, they have kind of a cloud layer in there now, I believe, when you go through, so you don't see that transition as much. But when I first made a video about it, you could see it snap over from like this globe, very, very blurry kind of approximation to an actual photograph. And so it's right there. It's a little complex and complicated, and I don't know exactly how they work it out in the South, because you do have somewhat of a problem with the breadth of the longitudinal distances with the GPS mapping once you get really far south in the southern latitudes. But there's so much ocean, and conveniently so many people live north. Like, what is the percentage of the world that lives north of 45 degrees southern latitude? It's like 90
or 95, so, or 90, at least 90
here.
It's in the high 90s, I think. Even it's a tremendous amount of people that lives. So the number of people and then the amount of travel is so little, and there's so many anomalies with it. Obviously, I think they do it mostly in the oceans. I think they do it mostly in the Pacific. Beyond that, I don't know exactly, but it's definitely not, what they present is definitely not a differentiable manifold. There's definitely a fudge factor in there, and it's much more than just differences in topographical elevations. It's far beyond that. So anyway.
I think at the poles, they have a lot of leeway to sort of tuck away corners and fudge it even more so. And then, of course, out in the middle of the ocean, there's a lot of room for them to tuck away, excess space or whatever. And so they have a lot of leeway on that globe, and it's going to be pretty difficult for your average Joe to travel to either the poles or to the middle of the Pacific or whatever to verify these distances.
And this is a three-dimensional mapping from all data sources using GPS. So this is the true map. And so one thing that was done, you took a look at the coastline, and you can plot it in 3 dimensions to measure the distance of the coastline, which is a fractal. It's impossible to do, but just from the data points available, thousands of data points, you can see the coast of California. And the really interesting thing about it is when you manipulate it in 3 dimensions, this thousands of miles long coastline, I think it's 1,700 miles, just that portion of California. I guess it's more than the highlighted section there, but look, when you plot it out in 3 dimensions, you can plot the distance here, okay, and it matches up with what maps say, so you know it's correct. But the interesting thing is when you look at it from the side, which we'll do here, you can see, well, there should be a lot of curvature, shouldn't there? There should be a lot of curvature. 2 million meters, and we'll calculate that here and see if we see that amount of curvature. And we'll calculate it's 1,283 miles. Okay, so let's see how much curvature. 108,000, almost 109,000 feet, or 206.2 miles. So 206 miles should be visible from the side. So let's have a look-see. It should be a very easily detectable crown. But no, look, pixel for pixel, it's straight across. Straight as an arrow, perfectly straight. Flatter than a pancake. Flat. Flat. Now this is actual map data. They say, go get a map, where's your flat earth map, blah, blah, blah. This is it, boys and girls. These are the data points from which the Google map is made that is navigable. This distance cannot be wrong from any direction. Therefore, if there's a curve, it would have to be visible.